Welcome to Utilizing AI, the podcast about enterprise applications for machine learning, deep learning, and other artificial intelligence topics. Each episode brings experts in enterprise infrastructure together to discuss applications of AI in today's data center. Today, we're discussing expanding ML models beyond the current limits with Dennis Abts of Groq.
Hi, I'm Dennis Abts, the Chief Architect at Groq. Nice to be here.
And I'm your co-host, Chris Grundemann. I'm a consultant, coach, and mentor, and you can check out everything I do at chrisgrundemann.com.
And I'm Stephen Foskett, organizer of AI Field Day and publisher of Gestalt IT. You can find me on Twitter and other social media networks at sfoskett. So Dennis, one of the things that we've talked about quite a lot on the podcast in the last two seasons is the fact that AI models are expanding in terms of the amount of data that they're utilizing, as well as the reach of this data and location of this data. But it seems that there are natural limits to the size of ML models. In other words, there's a point where you can have too much data to make it work. What are those limits? How do we decide when an ML model is just too big?
Well, it's a great question. I think there's really two kind of two ways to approach it, and as we've seen in the last several years, it's been really this voracious growth of models as they get as they get trained, and specifically, for example, natural language processing models like GPT-2 and GPT-3 are great examples, where the corpus of data and the number of parameters is in the hundreds of billions, and where the amount of time it takes to train the model like that is measured in weeks and millions of dollars to train it in terms of the energy cost, just the energy cost, not to mention the scientist cost and the fine tuning and all the things that go into getting it right, and the firefighting that go into bringing a model into convergence so that you can deploy it in the cloud. And by deploying it, I mean you can actually take that model now and the parameters that you've learned and actually put it to good use. And that deployment process is often one that it can be very expensive, right? So there's this process of distillation that we go through, and it ends up being kind of a seesaw, like a sawtooth kind of waveform, where the models are really big, and then we shrink them with distillation, and then we train new models that are even bigger, and then we shrink those, and that process has been kind of this almost like simulated annealing that we've been going through over the last several years as we increasingly grow models into the trillions of parameters, and what that means for increasing amounts of data, and that's really some of the limits of scalability. And we see a number of big systems today. Right now, there's a system that NVIDIA makes that's called Selene. They build it as a reference, basically a reference supercomputer, and that serves as an example of a large-scale system that one could build to be able to do training on it. And right now, Selene, for example, I believe is rated one of the top 5 supercomputers in the world based on just its performance on LinPack. But it's really kind of it demonstrates just the onerous, the amount of computational power that you need to bring to bear in order to train some of these really large scale models.
So you talked about both, size of the model, right, in bits and bytes, or lots and lots of bytes in this case, and also some computation. What are the other dimensions of scalability when we're talking about ML models, both training and deployment?
Yeah, there's a number of dimensions of scalability. For example, I like to use the example of GPT-3 as a nice example where we can train this model, and then to use it, you actually have to infer on it. And it gets used in a variety of places. But for example, just using it to do email completion, for example, if you're typing an email and it's going to complete the remainder of the sentence, and that's a query into the predictive model. And if that, for example, if you do that inference, and if it takes 8 seconds for that inference to complete, that's not very practical if you're trying to actually do something in real time or quasi real time to be able to use it. So in other words, there's some scalability issues that creep into the deployment of these models, and those usually give rise as a result of service level agreements, in that the cloud provider or the application provider has some goals about the response time that they want to be able to deliver, and that those kinds of scalability and computational complexities bump into those kinds of service level agreements. And for example, if it takes if it takes 8 seconds for it to complete a sentence in your completion, it makes it really impractical to use that as a large scale deployment and a usable tool, right? So there's been more interest in scalable deployment on the inference side. In fact, if you've seen the keynote from GTC from Jensen, there's one of the areas that they're growing into is essentially multi GPU inference to try to reduce the response time. In other words, and when you scale your application, there's a number of ways you can scale it. You can scale it so that you want to do larger problem sizes. In other words, kind of strong scaling. You want to take the amount of work that you do and increase it so that you can get more work done. Or you can try to scale it up so that you can get more work done per unit of time. In other words, you want to get more throughput. And so there's a variety of ways you can kind of try to scale your problem so that you can fit usually within some fixed time horizon, as an example.
I think many people would have assumed that this conversation was just going to go straight to deep learning and talking about training, but it's interesting that you're going to inferencing. How large are we going to see the models on the inferencing side get in practical respects? Because the things that you're bringing up are going to be true almost no matter what the infrastructure is. I mean, we've all thought about this with, AI in the cloud, where there's only so much data that you can transfer. There's only so much, latency that you can tolerate. So that does seem to put a limit on the size of inferencing.
That's right, and for a very practical reason, these tend to be kind of like liquid. Liquid fills the size of the container. Data is the same kind of thing. It fills the size of the GPU or the TPU on which it's running, right? And so these kinds of things will be deployed, and the container, so to speak, is essentially the memory footprint that we can fit in that model. For example, if it's 40 gigabytes of GPU memory that you have to fit in, that's kind of the container you have to live within. And so there's an element of practitioners and model designers have to live within the containers that they have. And in a sense, you go to war with the weapons you have, not the ones you want, right? Ideally, we'd love to have hundreds of gigabytes available on each node, but in reality, that's just not the case. And so, given those kind of constraints with smaller memory footprints, that really brings to bear the size of models that you can really deploy. And deploying models is really a scalable question, a question of scalability, because when you deploy the model, you're going to be deploying it, for example, if it's a translation model, you're going to be deploying it in different languages, English, French, German, and so forth. And that takes up compute resources as well as, model designer resources, the people times, site reliability engineers, and so forth.
And as we've discussed quite a few times as well, we're starting to see models being deployed from an inferencing perspective on all sorts of hardware and all sorts of locations. So we're not just talking about 40 gigabyte GPUs in the data center here. I mean, we're talking about smaller devices. We're talking about edge computing. We're even talking about mobile devices. I mean, is that the topic that you're bringing up? Or are you really focused on the sort of centralized processing?
So it's a great point, and that scalability really affects a variety of things, right? As a model designer, if you want to bring to bear a new model and deploy it at the edge, well, that might be anything that's running an ARM processor from a printer, for example, an embedded processor in a printer, or a Raspberry Pi at the low end, all the way up to a supercomputer or a cloud instance, a large memory cloud instance. So there's a variety and a wide breadth and scale of different hardware options on which these models are deployed. And often these kind of state-of-the-art models really get deployed on state-of-the-art hardware, right? These are really very typically computationally intensive kind of problems. And the rule of thumb I typically use is for training, it's generally 8 to 10 times more footprint in terms of model complexity and model size, just to carry all the intermediate gradients that are part of the model. Because after all, it is gradients that make the world go around. It's not money that makes the world go around. It's gradients that makes the world go around. Or so I tell my daughters anyway. And so it's really kind of a fascinating spot that we find ourselves in building these models and then deploying them in all sorts of different areas. And to your point, there's places for which it just doesn't make economic sense to deploy a model. For example, a model that may simply be too expensive to deploy it at scale on some form factors and some platforms where it just simply may not make sense given the requirements and given the constraints of that edge configuration, for example.
Yeah, that's certainly fascinating. And to both those points, it sounds like in this case anyway, in all cases, right? In many cases anyway, scalability is both scaling up and scaling down, and there's a limit to both. I've personally never worked in an environment that was completely unconstrained resource-wise, right? There's always been some kind of limit, whether it was dollars or space or cooling or power or something that was a limiting factor. I'm sure there may be some deployments somewhere that are beyond that, but I've never built one. So within that, right? I mean, obviously, some of those things are some of the factors that are obviously challenges with scaling, both up or down. Maybe you could talk a little bit more about other current challenges with scalability in general.
Yeah, we find ourselves in this brave new world of what I'll call converged HPC, which is really, I think of it as take all your conventional high performance computing type of codes. I mean, old things that are built on Fortran 77, all the way up to more modern climatology codes and COVID models, for example. And there's a lot of discussion in the HPC community around really how expensive that 64-bit data type is. And really this converged high performance computing is really looking at HPC from the perspective of what can you do with these lower resolution data types that are, for example, 8 bits or 16 bits wide to supplant or act as a surrogate or proxy for these wider data types, these 64-bit values, where if you need the dynamic range, that's fine and they're there and you can use them. But if you really don't need all the precision that those 64 bits are delivering you, there's a very real performance cost, power cost, and area cost of deploying models with those kinds of data types. And so what we're finding is that instead of, for example, if you're doing finite element analysis, or if you're doing, for example, non-destructive detonation of a bomb, and you're computing all the Navier-Stokes, you're computing the Navier-Stokes equations to compute all the different elemental interactions of all the particles, is very computationally expensive. But we're bringing to bear machine learning models in a way that allows us to predict what the end result of, for example, an explosion might be. So you don't have to do all the part by part finite element analysis. You can just kind of go to the punchline. And that's really an exciting thing as we move forward with this converged HPC. We're going to see several orders of magnitude speed up in what I'll call classical simulation or conventional simulation tools, where you're able to use both conventional classical methods of that, as well as machine learning models where you're predicting where to go to next, for example. A good example of this is state space exploration, where you might be exploring the state space of a fluid dynamics model. And in one part of that state space, it's metastable. So you don't want to go into that part. And so you can use your predictive models, your machine learning models as a sort of scout to make sure that you're exploring the state space in a productive way. And you don't end up encroaching in some strange little corner of the model that pushes you into a metastable weird state where, for example, the physics break down and they don't work anymore. So there's all sorts of really creative ways and neat ways that are being brought to bear that I think land squarely in this area of converged HPC that certainly admit to the scalability problems. Obviously, large HPC machines that are national resources, like Oak Ridge's Summit supercomputer, those are tens of thousands of nodes, and they're national resources with many NSF scholars using them for a variety of computational science, from biology to COVID and drug research, for example. So it's really an exciting time, not only from machine learning, but from high performance computing, and really this intersection, if you will, this Venn diagram over where those two intersect. As you can imagine, there's quite a lot of commonality between the two.
It's really interesting what you're saying about the sort of collision of HPC with artificial intelligence, because we've certainly seen a collision from HPC into enterprise infrastructure as well. So you mentioned Summit, for example. Summit showed the architecture that has now been deployed by NVIDIA Grace in terms of creating an NVLink linked CPU sidecar for GPU machine learning tasks. And I think that it is sort of indicative of how the entire industry is moving, not even just artificial intelligence industry, but the entire enterprise compute industry. We've been talking, for example, about the CXL technology, which will allow us to scale compute resources outside the box and so on. But it seems sort of a paradox, because on the one hand, we're figuring out ways of bringing HPC to bear to make our computers bigger. But on the other hand, we're actually taking the same HPC concepts to build, I don't know, smaller, bigger compute, if you kind of get where I'm going with that. So, you've got Summit with all its, thousands and thousands of GPUs. And then we're taking that architecture and building something with tens of GPUs. So it seems really interesting that we're building bigger systems in a smaller way. We're sort of smaller instantiations of bigger systems. And one of the things too that you brought up was this whole idea that we're starting to discover that some applications perhaps don't need the precision that we had been using previously. We've seen studies of that, and we've of course heard from companies like Intel and recently BrainChip talking about how you can use lower precision. Does this sort of put a monkey wrench in your scalability claims? Could it be that we're going to solve the scalability problem simply by using lower precision ML on smaller systems?
Very good points. In fact, you're right. We capture that the additional precision that we get comes from the hidden state, the hidden layers in the model, right? So you can think of it as really a trade-off. We're not losing that precision necessarily. We're replacing it with different types of state that capture the essential qualities of what that quote variable would be capturing if it were in a 64-bit data type. But you're absolutely right in that we're building these large heterogeneous supercomputers, but we have a need to carve those up into smaller units of, call it smaller granularities, so smaller atomic units of compute that we can deploy at a smaller scale, but more of them. For example, when you do deploy your model, you're going to want to deploy multiple instances of it so that you can have throughput, obviously, and that it takes cost and power and resources to be able to do that, as you point out. So yeah, there is definitely kind of these push and pull kind of compromise and trade-offs, we'll call it, for lack of a better word. And this is where different architectures can shine and show their ability to scale. As you kind of pointed out, the NVIDIA GPUs more recently have the ability to scale up and to create larger what's called a shared address space, a PGAS address space, a partitioned global address space that they all share. And that allows them to be able to essentially do that, what I talked about earlier, biting off more, being able to process a larger chunk and be able to do more capable things. It reminds me of one of the expressions that Jim Smith was a computer architect at Cray Research. He used to say, if you have a vector problem, you're always best served to use a vector processor on a vector problem. And the same thing really applies for a tensor problem. If you have tensors, you want to use a tensor processor. for the same reasons that make graphics processors really good at doing graphics, right? If you're pushing polygons around a screen, there's nothing better than a graphics processor for that. So it really brings to bear some really interesting architectural trade-offs that you see in the marketplace across different hardware providers, different system architectures. For example, the Groq system allows you to build a multiprocessor from their chips just by connecting them up. It's kind of a glueless multiprocessor in that there's no additional hardware is required. In other words, it doesn't use an additional external switch or anything like that. It literally uses just the chips that are included in the system. So there's no additional complexity, so to speak, of building out these systems. Like for example, NVIDIA uses NVLink, and they have larger, fat tree topologies and fat tree networks that you can make from that. And all of those introduce additional complexity in the system complexity, as well as it reduces the reliability. And what I mean by that is, as you start to kind of grow these systems, you can think of it as they become a little bit brittle in that you have to keep everything functioning at the same time. I think of it as it's kind of like trying to pull the plow. If you're trying to pull a plow, do you want to pull it with one big ox, or do you want to try to pull it with 7,000 chickens? And when you're working at scale, right, you have 7,000 chickens, and you have to keep them all pulling and synchronized in the same direction. And that's difficult. And you start to bump into what I call Amdahl's law effects, right? Where you start to hit diminishing returns. And it's one thing to uncover some thread level parallelism. It's totally something different to uncover 7,000 way thread parallelism, or 7,000 way on just a single chip, for example. And then you put multiples of these chips together, and now you're suddenly looking around trying to discover 70,000 or 100,000 way parallelism. That becomes very, very untenable from a scalability standpoint. So there's some first principles kind of here to really look at how does the system scale, and how do you make it so that when you scale from 1 to 64, that you're getting good kind of linear scaling at those system sizes.
Yeah, I appreciate that. I love that metaphor, because that is kind of what I was trying to get at. Like, we're hearing sort of conflicting messages from the industry, with some people saying, oh, it's not a problem, we'll just lash together a bunch of tiny nodes or chickens, and other people saying, no, we need big, strong oxen here in order to pull this forward. Is it is it just simply a question of the data types being used? I mean, are there some data types, for example, that are going to need an ox instead of a bunch of chickens?
That's a great question. Yeah, unfortunately, there's some truth to that, right? Larger data types like FP32 and FP16 or bfloat 16. If you just think about the energy consumption of an 8-bit ALU operation compared to a 16-bit and a 32-bit operation. If you look at an add instruction, and this is really into the weeds, so I apologize, but I think it's important. If you look at this kind of an 8-bit versus 16-bit, even though the data type is twice as wide, it's quadratically more complex in terms of its area and power consumption. In other words, when you plop down an FP16 ALU, it's 4 times as expensive as plopping down an 8-bit ALU, and an FP32 is again double that. And so these things have a way of really compounding and adding complexity and area to the design, and to the ultimately to the system in which they're operating. And we see a lot of these trade-offs happening in practice, right? Tenstorrent, NVIDIA supporting 4-bit data types. We're going down at toward the low end. It reminds me of a lecture Richard Feynman gave that was titled "There's Plenty of Room at the Bottom," right? And that kind of applies to data types as well. Of course, that wasn't what he was talking about at the time. He was talking about nanotechnology and really exploring the spaces of quantum effects and what has emerged from that. But really, it applies to data types as well, and that's kind of the fun thing. If you take this to its absurdity, to its extreme, you can go down to a single bit, right? Binary net. You can take this down to just using the essentially the sign bit as the encoding, and it surprisingly it works, right? It's all part of a trade-off, but those kinds of things are really there's a lot of hyperparameters that are available to the model designers, and sometimes it's a little overwhelming. You almost want to have kind of a Costco model where you walk in and you only have 4 choices to pick from, not 4,000, where you can tune your hyperparameters in a way that it is fairly straightforward and reasonable to reason about the correctness and the performance of the model.
So it was a while back, but something you said really struck me. And as we're talking about data types and things, what part of my head jumps to use cases and how we actually use these data models. And there was a phrase you used, I think it was non-destructive bomb detonation. And I just want to take a second to roll back to that, because I think you're just talking about simulating explosions, right? But the turn of phrase was really interesting. And I wonder, if there's a spectrum of use cases that follow along, what can potentially use, sine wave encoding versus FP32, and kind of what are the barriers there? What's that spectrum look like from like real world enterprise applications?
Yeah, and it's a great question, and I think it's actually an ongoing and fertile area of research, right? Is because we're trying to discover and find the new areas in which we can really apply these new techniques. For example, there's using GAN models. GANs can be used to take a 2D picture. For example, I forget what NVIDIA calls this technique, but they take a 2D picture of it and they basically render it as a 3D model in the environment, and allows you to kind of fake a bunch of things and interpolate a bunch of results. And that's really bringing to bear new ways of applying this, and new ways of applying physics rendering and exploring the way that we think about and really model the world around us, right? Instead of modeling the world around us using the classical Newtonian physics, we're going to be teaching a model how it works. And that's our ground truth, is empirical physics, right? It's kind of like experimental physics is really the ground truth. Everything kind of stems and emerges from that in the same way. And I think that's really kind of a nice regime to be operating in, and that is your ground truth, and that's kind of everything else that we see as part of our reality is really the emergent property of those fundamental rules, and we see that with AI and training with these large models. It's really this whole concept of software 2.0 is really kind of an exciting time to kind of see where its niche applications are, as well as its broad applications. And the example of kind of bomb detonation as one example really applies to a bunch of different physical spaces. Anywhere where you have a physical representation of the world that you want to take it and decompose it into its 3-dimensional components. And I think a good example of this is, I think, climatology, right? We take climatology code, we break up the globe, we break up the world into its 3D components, we model everything in terms of its pressure, temperature, and volume, and its various physical properties. And we see that same kind of thing, and we can bring to bear these same kind of techniques to be able to simulate climatology. And I'm really, quite excited about what machine learning can bring to bear for climatology. And for example, one exciting application that I'm looking forward to. We've had a lot of wildfires in the United States, and one thing I think is an exciting application of AI is the old proverb, if there's smoke, there's fire. Well, we can detect this smoke using satellite imagery, and then be able to run a machine learning model to actually do smoke detection. Think of it as a global scale smoke detector, right? And it's kind of your early warning way of being able to hone in and pinpoint where the hotspot is, literally in this case. And I think we're running into all sorts of new applications where not only does it allow us to be a better guardian of the globe, better steward of our resources, but be able to improve our manufacturing processes by bringing to bear some of these techniques that we apply at a large scale. We can apply them at smaller scales in manufacturing, for example, looking at for defects in a bottling plant, for example. So there's a lot of different ways to kind of replace the physical processes that would have been computed with these new machine learning models that provide us with really many of the same benefits, but are really same great taste, less filling is kind of the way to look at it. That's a very Wisconsin thing.
It seems to me, the takeaway from this conversation is essentially that all these technologies, whether it's HPC or bigger, better, badder tensor processors, or distributed architecture, or reduced precision, or ML tuning ML, all of these things, the takeaway is that we're going to be using more data, bigger models, and we're going to be able to tackle things that we never thought we could tackle before, like global climate prediction and things like that, that were just too big, but we're building systems that can process them. Is that the takeaway that I should get from this conversation?
Yeah, I mean, there's several good analogies about, data is like the petroleum or the oil resources, and that labeling of data is like the refinery, right? And those who have the resources here, the oil and the ability to refine it, are in a unique position to take advantage of that energy density, so to speak. And that's a great example, because I think that if you look at the forerunners and the thought leaders in this space, it's research communities like Google, DeepMind, and Microsoft Research that have these huge corpus of data, and they have the ability to test out their ideas at scale before they deploy them. And that's really, like I said, that the data and the having access to data at their fingertips is really the powerful component, and that allows you to take advantage of, in this new software 2.0 kind of world, to be able to build better models, train better models, to be able to deploy those models at scale, and that is a really strategic advantage.
Well, I do appreciate that. And I think that that's actually a great way to leave the conversation. We do have to wrap up here, but before we go, we do have a fun little tradition of asking our guests to answer 3 questions for which they are totally unprepared. And so, Dennis, it's your turn. And I have a few questions here. Now, they're pretty much the same questions week to week, but I do try to shuffle them up and pick some that are appropriate, or at least something that I would get a fun answer for. So, Dennis, it's time. As a reminder, there's no right or wrong answer. It's just sort of a let's predict the future here. So here we go. First things first. In terms of assistance, you did mention voice assistance and latency and things like that. So how long will it be until we have a conversational voice-based AI that can pass the Turing test and fool an average person into thinking they're talking to another human?
Wow, great question. Conversational AI is taking some great strides forward. I think Jarvis is the technology that NVIDIA calls their new conversational chat and bot kind of technology, and it's really bringing to bear new techniques, including tone and inflection and sentiment. Instead of sentiment analysis, you can think of it as sentiment expression, expressing sentiment through voice. And that's making it even more difficult to be able to detect kind of subtle intonation that only comes from, frankly, from human vocal cords, right? And that kind of subtle inflection. Well, those kind of micro expressions and subtleties are now starting to be able to be expressed and controlled through AI, and I think it's becoming increasingly difficult, and we will see more technology and more models that are essentially trying to ferret out the deep fakes, right? And the better this gets, the more difficult it becomes. So bringing to bear some new techniques to be able to detect and identify ground truth, so that we as consumers of these things can have confidence that what we're looking at is indeed, either generated from the real world surroundings, or if it's just a figment of some machine learning model. So I expect in the next 2 years to have really the kind of sentiment analysis and sentiment expression that will make that type of conversational chatting with AI very almost imperceptible in terms of the ability to tell if it's real or if it's Memorex, I guess, to borrow an expression from the 80s.
All right, new question here. Will we ever see a Hollywood-style fake mind? In other words, Mr. Data or similar AI?
Great question. So, will we ever bring to bear kind of an android, so to speak, that would be able to kind of articulate and encompass? I actually think that we will, and I think there's strides happening in the neural interface area that will allow us to take those steps perhaps sooner than we ought to. But I think we will see tighter integration with that kind of computer brain interface. And largely, I think the initial applications will be medically inspired, and use cases will be for example, for treating Parkinson's or epilepsy or other aspects of degenerative diseases that can be staved off through technology applications. So I do believe that within the next 5 years, say we will have that tighter integration, and by that time we may see Elon Musk walking around with a third eye or something like that to kind of encompass that.
All right, final one. We talked big, so let's talk small. How small will machine learning get? Can we have ML-powered household appliances? How about toys or even disposable ML devices?
Fantastic question. When your toothbrush has ML embedded in it, I think we've arrived, right? You take all the ubiquitous things that you do in life, and when your comb tells you that you've only brushed your hair 13 times rather than the traditional 27 times on average, then maybe we've got problems as a society. But I think it's certainly getting to that point, right? I bought a toothbrush that actually has AI in it, and that they which is a little scary, right? They actually characterize your brushing habits, your tendencies, and they in a sense kind of turn your mouth into a set of features that they can look at, and that's a little alarming at some point, but I think that's coming, right? Before long we will have them integrated into our glasses, and in fact we see this today, augmented glasses with a variety of electronics embedded in them, and these will become our kind of viewport into the world. And they will be not only recognizing and identifying objects for us, but they'll be able to extract technology and be able to extract details that our brains may not be able to detect. For example, infrared or other electromagnetic frequencies that we can't endemically pick up. So I think it's an exciting new area that we will see greater and greater integration of machine learning into smaller and smaller form factors, to the point where you're going to say, hey Siri, and your glasses are going to wake up and respond to that.
You heard it here, folks. First, folks, your mouth is a feature store. Get ready for it.
That's right.
So thank you so much, Dennis, for joining us today on Utilizing AI. Where can people connect with you and follow your thoughts on enterprise AI and other topics?
Look me up on LinkedIn. You can find me at Dennis Abts, ABTS, on LinkedIn, and that's my preferred social media outlet. So I look forward to connecting with you on that.
How about you, Chris? What have you been up to lately?
Yeah, lots of fun stuff. I also enjoy having conversations on LinkedIn, so find me there. You can also follow me on Twitter at Chris Grundemann, or for all things that I've been working on and doing lately, chrisgrundemann.com always has the latest.
All right, very good, Chris. Thank you. And you can find me at techfieldday.com, and you can find my writing at gestaltit.com. And as I mentioned, you can also connect with me on most social media networks at Foskett. One thing I will call attention to is next week is AI Field Day #2. So if you join us on Thursday and Friday, the 26th or the 27th and 28th, you'll see some great presentations about enterprise tech and enterprise applications of artificial intelligence. So please do head over to techfieldday.com next week and check that out. So thank you for listening to Utilizing AI. If you enjoyed this discussion, please do remember to subscribe, rate, and review, as always. And please, of course, share this discussion with the rest of the AI community. This podcast is brought to you by gestaltit.com, your home for IT coverage from across the enterprise. For show notes and more episodes, go to utilizing-ai.com, or you can find us on Twitter at utilizing_AI. Thanks, and we'll see you next time.